Okay, so the first thing we looked at was annuity, and we were starting with a present value of $0. We were starting with $0 and we were making regular payments, and we were figuring out what the future value of that annuity would be. Now we're kind of working the opposite way here, and we're going to talk about present value. So when we talk about present value of an annuity, going in this direction, we are going to start off with a certain amount of money and our future value will be 0. So we're going to be taking out a certain amount of money. So present value of an annuity. Present value of an annuity is the amount that needs to be invested today to provide for regular payments of an annuity. So examples of this: at the time of retirement, the amount that has been saved to pay yourself on a regular basis, an amount donated to pay out an annual scholarship, a settlement pays out monthly, lottery or insurance settlement, and borrowing money and paying it back with regular payments. Okay, so like I said, we're starting off with a certain amount of money, and that amount of money is gonna go down every single payment that we have, or any withdrawal that we have. Okay, so we have our formula here. So our present value is equal to R times 1 minus 1 plus I to the exponent negative n over I. Okay, so here all of our values mean the exact same thing as our annuity formula that we've already used. So our present value is the amount we want to find, the starting amount of money we're going to have. Our R is our payments, our regular payments, or our regular withdrawals. Interest, we're going to still calculate that the same. So our percent we want to change to a decimal, and we're going to divide that by the number of compounding periods we have. N is our number of payments. So that one's going to be our number of compounding periods times our number of years. Okay, so looking at an example here, how much money would you need to be in a retirement account with an interest rate of 8% compounding monthly at the time of retirement in order to pay yourself $3,000 a month for 25 years? Okay, so our R value, that's our payment, and we want to pay ourselves $3,000. So R is 3,000. Our interest is the 8%. We divide that by 100 to get to our decimal, and it's compounded monthly, so we are also needing to divide that by 12. Okay, so 8 divided by 100 divided by 12. Is 0.00666667. Okay, you could round that to be less of a decimal if you'd like to. Okay, keeping in mind the more decimals you keep, the more accurate it will be. Our N value is our number of years times our compounding periods, which is monthly, so 12. So 25 times 12 and we get 300 for our N. Okay, so we're plugging all these values into our formula. So present value is equal to 3,000 times 1 minus 1 plus 0.006667 66667 to the negative 300. And that's over our interest, 0.00666667. Okay, doing your order of operations, you're going to solve what's in the bracket first. So the 1 plus the interest there. And then we're going to do that to the exponent of negative 300. It's going to be 1 minus that number times 3,000 and divided by the interest. Okay, so we get a total of $388,693.43. That's how much we're going to need in our retirement account. Okay, so therefore, we need $388,693.43 in the retirement account. Okay, so that's using the formula, and we're going to look at examples for using the TVM solver as well. So using that same TVM solver, calculating our values the exact same way. It's just we're going to be solving now for our present value instead of solving for our future value. Okay, so Victor wants to withdraw $700 at the end of each month for 8 months, starting 1 month from now. His bank account earns 5.4% per year compounded monthly. How much must Victor deposit today to pay for the withdrawals? Okay, so the amount of withdrawals Victor is going to make is 8. This is going on for 8 months, so our N value is 8. Our interest, remember you don't have to convert this, so we're just putting the percent of 5.4. Our present value is what we're going to solve for. Our payments, that's the withdrawal of $700. Remember, when you have a payment, you want to put a negative number there, so negative 700. Our future value is when we're going to end up with 0, so we just need the proper amount at the beginning, so there's enough there for the 8 months. So the future value is 0. And this tells us it's compounded monthly, so our payments per year and our compounding periods per year are both going to be 12. Okay, so now going over to the solver, we're putting in those values. And we're going to hit solve for PV, the present value, and we get $5,488.28. Okay, so how much must Victor deposit today to pay for the withdrawals? He will need to deposit the $5,488.28. Okay, we'll look at one more example. Joey would like to have enough money saved so she can withdraw $7,500 every 3 months for 25 years. Starting 3 months after she retires, how much must Joey deposit at retirement at 9% per year compounded quarterly to provide for the annuity? Okay, so every 3 months, that is saying quarterly. So that's 4 times a year times the 25 years for our N. So our N is 100. Our I is our percent, which is 9%. Present value is what we are solving for using our TVM solver. Our payments, we're withdrawing 7,500, so we want a negative 7,500 here. Our future value is when we're ending at 0, we don't have any more money left. And our number of payments and our compounding periods per year, quarterly, so those numbers are both 4. Okay, so if we go over to our solver again, putting in our new values, so N is 100, I is 9, present value we're solving for. We have a negative 7,500 for payment, future value is 0, and payment and compounding is 4. Solve for present value. And we get $297,313.05. Okay, so present value, $297,313.05 is what needs to be deposited at retirement to have enough money. Okay. So using that new formula as well as the TVM solver, you're going to answer these questions here. Please let me know if you have any questions.